In the AC mains window, you can identify the voltage of the grid you are connecting your PV system to. The power company or third parties deliver electricity at plus or minus 5%. So as we see here, you can consider 220 volt, 230 volt and 240 volt to have the same voltage level. The same goes for the 120 volt. You can consider 110 volt, 120 volt and 130 volt to be at the same level. You can choose a number of phases, and I know that some might ask about what is split phase. So split phase is a two phases voltage system. It consists of two phases that are shifted by pi or 180 degrees. Here we can see 120 volt split phase system with line to neutral voltage equal to 120 volt and total voltage difference of 240 volt across the two phases. They are also called single phase 3-wire systems or split phase. They are called split phase as they are the same as if you split a phase into two halves and ground the center of the phase. Now we have two hot wires and a neutral or cold wire. And so they are called 3-wire system as we can see here. So the difference between the system and the single phase is that the single phase has one neutral and one hot wire. Next, you have to provide the displacement power factor. It's the same as the apparent power factor or the ordinary power factor that we already know before. It exists due to the shift between voltage and current as a fundamental frequency. How can you measure the power factor? You can use a wattmeter, voltmeter, or meter method to measure the power factor at the site. This method only works for balanced systems as the power factor of balanced polyphase circuit is the same as the one at any phase. So you can measure the power through a wattmeter at a phase connected to a load, so we can divide the wattmeter reading by a meter reading multiplied by the voltmeter reading. So we obtain real power over apparent power, which is equal to the power factor. However, in an unbalanced system, you could measure voltage and current at each phase separately. Also, the same goes for the power. Then get the average value to yield an average lagging or leading power factor. Note, if the power factor is 92% or 0.92, you have to oversize the inverter by 8%. The software do it automatically if you let the software suggest an inverter, but why would I need to do this? In most countries, rules require you to supply reactive power, and to make the network stable, you have to establish balance between the PV system and the network. If a network charges only for a power factor of 98% and you have to work on a 98% power factor or pay for a penalty, then 98% of the apparent power of the inverter can be used as real or active power. So you need 2% more power to supply the reactive power. Let's have a simple example. An inverter is set to supply power at 0.92 power factor. The inverter is 8 kilowatt power, then actually 7.36 kilowatt, which is 8 multiplied by 0.92, is the real output power of the inverter. Now, the network has 92% of its power active power and 8% of its power reactive power. The output of the inverter is 7.36 kilowatt and it's pure active power. Then the inverter needs extra power to supply the reactive power. The settings of the inverter has limited the inverter power to 92%, then we need extra 8% over the 8 kilowatt power. So if we set the inverter to 92% of its power to be delivered to the grid, we get 8.64 multiplied by 92%, which equals to approximately 8 kilowatt of power. The power factor then is 92%, and we could use 8 kilowatt of power. So we have to select an inverter with 8.64 kilowatt rating, for example, to get 8 kilowatt necessary to operate our PV system. The maximum feed-in power clipping is used when there is restrictions that limits the AC output of the inverter or the power that is fed into the grid. So if you have any limitation for the output power of the inverter, as it have to be set to 70 or 80% of the input, or there is a maximum value for the output power that is fed into the grid, you can set it here. For example, an 80% limitation for 5 kilowatt inverter would yield 80% multiplied by 5 kilowatt, which is equal to 4 kilowatt as the output. So the rated power of the inverter is limited to 4 kilowatts. Another example to make things more clear is you install 50 kilowatt PV system and you are only allowed to feed in 20 kilowatt into the grid. And it's the maximum value. Then you set the feed-in power clipping to be 20 over 50 multiplied by 100%, which is 40% at the inverter. So if your system is working at its maximum, supplying 50 kilowatt, and there are no loads or no batteries, you could feed the grid with the maximum value that is allowed, which is 20 kilowatt. If there are loads or batteries, you have to set the limitation as a feeding point, so you won't affect the batteries and the loads by reducing the power flow to them and losing the inverter power. If you size the inverter and the panels properly and know the load and the battery's demands, and there are limitations to feed-in power, you can set it at the feed-in point here. It's the best to always clip power at the feed-in point so you won't oversize the inverter and increase the cost. Unfortunately, not all of the inverters are capable of doing so. Assuming the solar electricity or electricity from PV systems to contain nearly no emissions, you can calculate the emissions that you will get rid of through a simple calculation made by PVSol. For example, the emissions for CO2 from coal power plant that supplies electricity is 950 grams per kilowatt hour, and you will get rid of 950 grams per each kilowatt hour if you install the PV system. PVSol could calculate the total yield in kilowatt hour and how much emissions you could save by using the solar system. You could create a model to calculate emissions from PV systems and emissions from coal electricity and put the results in the emissions saved.